So the students found this problem in my lessons on in our PDFs and asked me to solve this question. And it was very difficult for us to determine the tangential acceleration in this problem. So I thought we will record this video for everybody to be able to see, because only a few people were with me in the Zoom when we were solving this question. So let's look at this of 1983 AP exam, AP Physics C exam in mechanics, and how we solve this question. So in this question, we have a particle of mass m slides down a fixed frictionless surface or sphere with radius r, starting from rest at the top, so there's no kinetic energy at the top, and it slides an angle theta. In terms of m, g, r, and theta, determine each of the following for the particle while it is sliding on the sphere. So we need to find kinetic energy of the particle, centripetal acceleration of the particle, and then the tangential acceleration of the mass. That's the one that we struggled to do in the classroom. So I wanted to do it because of on AP Physics in the AP Physics workbook for AP Physics 1, they don't include the 3 and B into the question, but they do include 1 and 2. And I think 3 and B is more AP Physics C than AP Physics 1, but 1 and 2 is the level of AP Physics 1. So I'm going to redraw the position of the mass on the top. So here is the mass on the top. And then it slides down. It doesn't have any velocity on the top, but it does have some velocity right here at this position. And the velocity is, linear velocity, is always perpendicular to the direction of, to the radius. So the velocity is going to be in this direction. And the length of this path is r, or this length is r. And here is theta. Now, if I look at, let me choose maybe one color, this one. If I look at these lengths right here, then if this whole thing is r, and this is theta, then from this triangle right here, the darker triangle, that part is theta. So if that part is theta, then this length right here is r cosine theta. And this length right here is r sine theta, because the hypotenuse is r. This one is the right angle, because that would be the x and y axis. So this would be the x-axis. And so this length right here, this one is r sine, and this one is r cosine. So then if I call this part h, if this is my h, then h is equal to r, which is the full length, this full length, minus the bottom part, which is r cosine theta. And if we say that on the top of the sphere, the object or the mass had potential energy, which is mgh, compared to the position at this height. Let's say right here, our position at this position, at this height, the potential energy is 0. Then the kinetic energy, let's call this point B and this point A. So the potential energy at point A is going to be lost to the kinetic energy at point B. So when they ask you what is the kinetic energy of the particle, then the kinetic energy of the mass is equal to mgh, and h is equal to r minus r cosine because h is equal to r minus r cosine. Then I have mg, and I'm going to take r out, and I have 1 minus cosine theta. So that will be my answer for the first part. So the kinetic energy is equal to mg r, and then I have 1 minus cosine theta. For the second part, I have to find the centripetal acceleration of the mass. Because the kinetic energy is equal to 1/2 mv squared, and that is at the point B, and then the mass and the mass can be cancelled, then I get that velocity at point B is equal to, or let's do velocity squared, is equal to 2 rg, and then 1 minus cosine theta. And I'm not going to solve for velocity itself yet. I'm going to leave it this way because they asked me for centripetal acceleration. Let me change it to a different color. So they asked me for centripetal acceleration, and centripetal acceleration has the formula of v squared over r. And in our case, this is our v squared. So if I divide that whole thing by r, then I get 2g 1 minus cosine theta. So that will be my answer for B, or for the second part of this question. So this was for the first part of my question. This is for the second part. And then for the next one, the tangential acceleration of the mass. So I redrew the picture of the mass moving along the sphere because I'm going to use in here something. But I want to talk about what angular acceleration is before I continue deriving the tangential acceleration. So angular velocity is the change of the angle over the time. And the angular acceleration is the tangential acceleration over the radius, or tangential acceleration is equal to r times the angular acceleration. So we know this part. And now I'm going to use the torque. So the torque is equal to the force times the distance that is acting on, this is like rotational motion, and equals to inertia of the mass around that sphere and times angular acceleration. And the force that is acting on the mass is mg. So I'm going to make it all the way till the x-axis, mg. And the distance that it is acting from the point of rotation, so if this is r, this is r sine theta, because this part is theta and that part is theta. So for the force, I'm going to have mg. And for the distance, I'm going to have r sine theta. For inertia of the mass, because I have to look at it as if it was a hoop, and for the hoop I have mr squared, and then I have angular acceleration. So I see m and r, and I see m and one of the r's I can cancel. So I have angular acceleration is equal to mg, or g sine. It is m is cancelled. So it is g sine theta divided by r. But also tangential acceleration is equal to r times angular acceleration. So the tangential acceleration is equal to r times g sine theta divided by r. So r and r can be cancelled, and tangential acceleration is equal to g sine theta. So we have this part. And for the last part, they ask you to determine the value of theta at which the particle will leave the sphere. So when I'm determining at which moment the particle is going to leave the sphere, I have to think about this part. So right here, I'm going to look at the forces that are acting on that particle. You have the normal force acting from the sphere, and you have the force of gravity. And because it's moving in a circular path, then there is centripetal acceleration. And because I'm solving always my diagrams when I draw them, I choose my x and y axis aligned with my acceleration. So I have to make it like this, perpendicular. So this is my x, and y is going to be aligned. So when they say it leaves the sphere, that means the normal force is going to be equal to 0. But I'm going to include it into my calculations. But I do need my x and y components of the force of gravity. So if I prolong it to the center, right here again, so that is your angle theta, because this was angle theta. And this is angle theta. So I have this part mg sine, and this part is mg cosine. So for my equations for the forces, I have the normal force is positive, minus mg cosine theta, and on y-axis I have acceleration equals to negative mac. I'm gonna also write the x coordinates for the forces, and because the mass started with no velocity all the way on the top of the sphere, it now has that velocity that we calculated earlier, v at the velocity b. So this was point A, this was point B, and we found that tangential velocity. So that means we do have tangential acceleration, the one that we just calculated right here, the formula for tangential acceleration. So I can write my equation for the x-axis as mg sine theta is equal to mat, mass times tangential acceleration. And here is another example that you can see that tangential acceleration is equal to g sine theta, so which gives you the same formula that we found a little bit earlier. Not sure which one would be the easier way to find it, but there are different ways to come to the solution. What I'm going to do is I'm going to use this top equation to calculate, to find what theta is equal to. Because at the moment when the mass is leaving the sphere, the normal force is equal to 0, and I also can cancel the masses or negative masses from both sides. What I'm going to be left is g cosine theta is equal to, and we found that centripetal acceleration is equal to 2g 1 minus cosine theta. So I'm going to say 2g 1 minus cosine theta. They both have g's on both sides, so I can cancel a g and a g. And then what I have is cosine theta is equal to 2 minus 2 cosine theta. So I can subtract or move all theta to one side. So I'm going to have 3 cosine theta here and 2 over there. Then cosine theta is equal to 2/3. And from here I can see that theta is equal to arc cosine of 2/3, 0.66, and that gives me an angle theta at which the mass is going to be leaving the sphere. And I get 48.2 degrees. And that is this angle, or that angle that we calculated, angle theta. And that's going to be it for 1983 AP Physics C problem related to rotational or centripetal motion. Thank you for watching, and I'll see you in the next video.